When we write a program, we're giving a computer instructions to perform some task. These instructions, such as if statements and loops, control the flow of the program. They let us make decisions and repeat actions. In this chapter, we'll break down and visualize what happens under the hood when Python executes your code. At its core, all a computer ever does to compute is run instructions one by one, in sequence. So every programming language, including our beloved Python, eventually turns your code into these machine instructions for the computer to execute. Our approach isn't a traditional tutorial on control flow. It's more detailed, but it'll give you a much better understanding of how Python and computers actually work. Along the way, we'll clear up the confusing boundary between compilation and interpretation regarding Python, and even answer some deeper questions from the theory of computation. For example, is there a limit to what you can do in Python compared to other languages like C++ or Rust? Different languages have different features and ways of writing code, and they may compile to different machine instructions. So it's fair to ask whether there are programs you can write in one language but not in another. Is there a limit to what you can do on one computer compared to another? Computers can have different machine instructions depending on their hardware architecture. So it's also worth asking whether there are programs you can run on one machine but not on another. We'll see that computers can compute anything that's computable, and that Python can express any computation through its control flow. In this channel, we bridge the gap between writing Python and shipping production-ready Python, covering the essential ideas and tools you need to get there. In chapters 1 and 2, we introduced Python's object model and its core data types. Up to this point, our focus has been on the static program state, the objects that exist, the values they hold, and how they're represented. We now turn to control flow, the instructions that inspect and update that state as the program runs. This is where programs begin to be dynamic. Together with mutable state, conditional control flow gives programming languages their computational power. To tell a computer what to do, your code has to be translated into machine instructions in binary format that the hardware can execute, and that translation can happen in different ways. If all of the code is translated before the program runs, it's called compilation. This is like translating an English text into French all at once before anyone reads it. If the translation happens statement by statement as the program runs, it's called interpretation, like a real-time translator who listens to each sentence and renders it on the fly. Python is an interpreted language, meaning it isn't compiled directly to machine code. The boundary is a little subtle because Python source code is first compiled all at once to an intermediate format called bytecode. That's what the .pyc files in your PyCache folders are, with the C standing for compiled. This bytecode is then interpreted, one instruction at a time, by CPython, the reference implementation of Python written in C. C, on the other hand, is a compiled language, so before any of our Python runs, the CPython interpreter itself has already been compiled down to machine code that runs directly on the hardware. There are many more compiled and interpreted languages, but in the end, they all run on hardware that executes machine instructions in sequence. Let's start with branching in Python, the if-else statement. An if-else lets us take different actions depending on a condition. Before we look at the bytecode in detail, let's briefly explain what a computer does. The central processing unit has a little working memory called registers. It has an arithmetic logic unit that does the math and comparing. CPU also has an instruction pointer that tracks what to do next. A larger memory holds both the instructions and the data they work on. The CPU reads the instruction the pointer is on, runs it, advances the pointer, and repeats. Instructions run one after another. Python's disassembler module shows the exact compiled bytecode the CPython interpreter runs. Think of bytecode as the CPython virtual machine's own instruction set, while the real machine runs binary instructions specific to its hardware. Throughout, we also show the assembly instructions in the text part of the running process. That'll be the compiled CPython interpreter itself executing our bytecode in a loop. We trimmed the bytecode of bookkeeping instructions to save screen space, and jump targets are written as labels like L1. The number down the left is the source line each group of instructions came from, and the color strips in the animation highlight this mapping. Now here's our first puzzle. An if-else has to run some instructions and skip others, but we just said the CPU only ever moves to the very next instruction. How can it skip ahead? The answer is one extra power we already see here, a conditional jump instruction. A conditional jump says, if this value is false, don't go to the next instruction, go somewhere else instead. Every branch is a compare followed by pop jump if false, which skips to the next branch when the comparison fails. If you follow the line numbers, you can watch the first jump land on the else if, or L1 at line 4, and the second land on the else, or L2 at line 7. The else if and else are simply the jump targets of the previous check. Machine instructions wield the same conditional jump power, which makes branching possible on any hardware. Our second puzzle is what else we can do with just conditional and unconditional jump instructions. As it turns out, pretty much all of computation. This is the essence of Turing completeness, and it deserves a video of its own. For now, let's see how the same jump powers while and for loops. Branching alone isn't enough to compute everything. We also need to repeat work, and for that, jumps again do the trick. Suppose we have a while loop. Let's reason it out as bytecode instructions. First, store 0 in x, then check whether x is less than 42. If it isn't, jump past the loop body to whatever comes after at L2. If it is, run the body, adding 1 to x, then jump back up to the check at L1. Pop jump if false is our conditional jump out, and jump backward is our jump back. So, a Python while loop is just a conditional jump to leave, plus an unconditional jump back to do it all again. A for loop is the same idea in a different form. Instead of checking a condition, it walks an iterator until the iterator runs out. For iter is the conditional jump again. It asks the iterator for the next value, and if there isn't one, it jumps out of the loop to L2. Otherwise, it binds the value, the body runs, and jump backward goes back to ask again at L1. Underneath, while and for are the same machine. The same trick also explains break and continue, the two ways to cut looping short. The break keyword leaves the loop entirely, and continue skips the rest of the current pass and goes straight to the next one. Take break. Break is a jump to L4, the instruction after the loop. Continue is its mirror image. It jumps back to L1 for the next value, skipping the rest of the body. Neither keyword needed new machinery beyond the conditional and unconditional jump instructions we saw. Next, we look at one of the most important control flow mechanisms in Python, the try-except statement. A try-except statement in Python lets you attempt something that might fail and handle the failure instead of crashing. If the user types a number, int parsing succeeds and the except is skipped. If they type something that can't be converted to an integer, int raises value error and control jumps into the handler. This style is often summarized as easier to ask forgiveness than permission. Rather than checking in advance whether every operation will succeed, you try it and handle the failure if it comes. It can read better and save defensive checks. You may have heard that try-except is slow and should be avoided for performance. On modern Python, that's a myth. In the bytecode, line 1, the try itself compiles to a single nop, short for no operation, an instruction that doesn't cost anything to run. Notice that the happy path runs straight through line 2 and returns. It never even touches the handler instructions below. Instead of branching, the compiler builds a separate exception table off to the side, a map that says if an instruction in this range raises, here's the handler to jump to. The cost only arrives when an exception is actually raised and the interpreter looks up where to go. So, try-except is usually fine to use for unexpected error handling. When an exception does fire, picking the right handler is itself a conditional jump. On line 3 of the bytecode listing, check exception match asks whether the raised error matches the value error you named, and if it doesn't, pop jump if false jumps past your handler to L1 where it's re-raised. Try except takes 2 more clauses. A finally block always runs, whether or not anything failed, which is what you want for cleanup like closing a file. The compiler guarantees this by copying the finally code into both the success and the failure paths. And try can take an else clause, which works just like the else on a loop. So let's look at both together. Most of us first meet else attached to an if, but Python also attaches else to loops and to try, and this overloaded meaning can be confusing at first. A loop's else runs only if the loop finished normally, without ever hitting a break. Here's the searching for 42 code from before, now with 42 removed from the list, so the loop runs to the end and the else fires. When the loop runs out of items, for iter jumps to L3, the else block on line 5, and the else runs. But break jumps to L2, which leaps over the else straight to line 6. This is the classic search and report pattern, where you either find a match and break or fall into the else to report that you never did. A try-else, like we saw earlier, is similar in spirit to a loop with an else. The else block only runs on normal completion, meaning it runs if the try block finishes, without raising and without exiting via return, break, or continue. Here's the full example from the intro one more time to mention a few compiler tricks that Python does. Line 1 starts with something odd. We wrote a list, but loadconst pushes the tuple 4, 8, 15, 16, 23, 42. This is an optimization that avoids the heavier overhead of creating a list at runtime. A mutable list would have to be rebuilt on every run, so the bytecode compiler converted our list into a tuple at compile time and stored it as a constant. We mentioned this in Chapter 2, Part 2 of data types before. In line 2, we see the load small int instruction, which is a special optimization for small integers. We saw this in Chapter 1, our object model video. The integers from 0 to 255 are pre-allocated and shared, so the compiler can load them directly without needing to create a new object. In fact, they live in the data section of the process, but we intentionally put them in the heap because that's where almost all Python objects live. For lines 3 to 6, you can watch the line column walk into 3, 4, 5, and then back out 4, 3. The f string is assembled right on the frame's value stack, with format simple, turning the value of n into text and build string joining the pieces at runtime. Notice there are only 3 pieces. The plain string on line 4 and the opening text of the f string on line 5 were merged into one constant, because Python joins adjacent string literals at compile time. So, the compiler does a lot of work to optimize your code before it runs. It folds constants, merges strings, and even inverts the logic of branches to keep the common path fast. But in the end, it's all just instructions that manipulate state and jump around. In this chapter, we saw that conditional and unconditional jumps make all computation possible. With modifiable state, branching, and iteration, you can compute anything that's computable. Some computations may run too long or need more memory than you have, but those are the only limits. This also answers the 2 questions we started with. Any language that gives you branching and iteration can express the same computations, so there's no program you can write in C++ or Rust but not in Python. And any processor with a conditional jump can run them, regardless of architecture. Languages and machines differ in speed, memory, and convenience, not in what they can compute. But what about functions? We use them all the time, and we just said we don't need them to compute anything. The reverse also turns out to be true. A field called lambda calculus shows that everything we just did with control flow can be done with functions alone. In the next chapter of our Python Before Production series, we turn to functions. See you there.